Hey Ramblers! This video covers section 4.1 in our textbook, but it's really the second half, so I'm going to refer to it as chapter 4.1 using first and second derivatives part 2. So we're going to learn to use the second derivative as a tool for sketching functions. And as you recall, the second derivative deals with concavity. So we will learn about the second derivative test, which is a test for maximums and minimums dealing with concavity. We'll also be introduced formally to inflection points, and we'll see that they are just a place on the graph where the function changes concavity. Finally, we're going to look at an example that wraps everything up together. So we'll use the first derivative to find maxes and mins and increasing and decreasing intervals, and we'll use the second derivative to find changes in concavity or inflection points and intervals where it's concave up and concave down. So please take careful notes, pause often, and work along. All right, Ramblers, thanks for watching, and I hope this helps. Let's look back at some of the sign patterns we've made, or at a sign pattern. And let's just take a couple of, let's take a point A and another one B. And let's say that the first derivative was positive to the left of A, that it equaled 0 at A. It was negative between A and B, it equaled 0 at B, and then it was positive to the right of B. That would mean that the original function, f of x, was increasing, hit a local maximum, possibly global, but we don't know. It decreased to hit a minimum, possibly global or local, we don't know, and then increased again as the derivative turned positive. Well, do you notice that by the virtue of the shape of the increasing decreasing, that this region here is concave down and this region here is concave up? So they've come up with a second test for finding maximums and minimums dealing with concavity. It's called the second derivative test. And it says, suppose there is a critical point at a continuous function at f of p. I've called those critical points A and B. So we're going to assume that at the critical point, the first derivative is equal to 0. Well, if f is concave up at point P, then there's a local minimum there. If f is concave down, then there is a local maximum at P. And looking up at the picture in the sign pattern above, or even at the examples that they have down here, you can see that that's true. On a region or an interval that is concave up, a critical point has to indicate a minimum. If the region or the interval is concave down, then a critical point has to indicate a maximum. Okay, it's called the second derivative test. It is as useful as the first derivative test. It really just depends on the information we're given. Okay, let's talk about inflection points. Okay, let's take a look at the definition of inflection point first. So an inflection point is an x value or a coordinate where the graph of a continuous function changes concavity. We've seen this before. Let's take a look at the very familiar curve y equals x cubed. We know that right there at the origin, I am changing from concave down when x is negative to concave up. Now, if we were to look at the derivatives, we had f of x equals x cubed. F prime of x equals 3x squared, and f double prime of x equals 6x. If I set 6x equal to 0, then I know that the second derivative equals 0 when x equals 0. And if the second derivative is equal to 0 or undefined, then we have an inflection point, as we do right there at the origin. Okay, let's take a look at one more definition. I think we don't want to skip over this idea of global max and global min, and then we'll take a look at an example bringing all these things together. This term really isn't presented formally by our textbook until the next section, but it's come up in class enough that it really doesn't make any sense waiting any longer. Look at the graph below. You can see that there is a local minimum on the left there. In the middle we have a local maximum, and then on the far right we have a local minimum again. But that last local minimum is also a global minimum. And by that we mean it is the lowest y value among all the local minimums. Now, this graph doesn't have a picture of a global maximum, but a global maximum would be the same thing. It would be the highest y value on the entire function of f. For instance, imagine if you had a parabola, an upside down parabola. The vertex point would be a local max, and it would also be a global max. So on each function there is at most one global maximum and at most one global minimum. There doesn't need to be either. And every global max or global min is also a local max or local min. Okay, let's take a look at one more example and then we'll wrap things up. Let's look at the function x cubed minus 9x squared minus 48x plus 52. Take a minute, pause the video, and write out the first derivative. Now the first thing we're going to want to do with this derivative is set it equal to 0 so that we can find the critical points. The critical points are going to be anywhere that the function is undefined, where the derivative is undefined or where the derivative is equal to 0. I'm first going to set it equal to 0, and let's factor out that 3 so that it's a little bit easier to solve. Why don't you take a minute and factor the resulting trinomial to find the places where the derivative is equal to 0. This factors to x minus 8, x plus 2, so the critical points are found at x equals 8 and negative 2. And if I make a sign pattern, I'll put negative 2 on my sign pattern and an 8, and I'll mark x and f prime of x. Now if I plug a large negative number in, or a number safely to the left of negative 2, plug it back into the derivative. Now I'm going to plug back into the factored form of the derivative because that's just easier for me to work with. If I plug a big negative number in, I can see that the first binomial is going to be negative, and the second binomial, if the number is less than negative 2, will also be negative. Since negative times a negative is a positive, we know the function is going to be increasing until negative 2. I'm going to plug in 0 for the next region, and if I plug in 0 once again to my binomial factored version of the derivative, 0 minus 8 is negative and 0 plus 2 is positive. So the region between negative 2 and 8 has the derivative is negative, which means the function is decreasing. And then finally, for large positive numbers greater than 8, that first binomial will be positive, and the second nomial will be positive. Positive times a positive is positive, and so my function is increasing there. That means that I have a maximum here at negative 2 and a minimum at 8. Since this is a cubic and it is increasing to infinity and decreasing from infinity, it's likely that this is only a local maximum and a local minimum. Alright, now let's take a look at the second derivative and see what we can find in terms of inflection points and concavity. Well, the second derivative, f double prime of x, is going to equal 6x minus 18. Now, since inflection points happen where the second derivative is equal to 0 or undefined, let's set that equal to 0. When we set it equal to 0 and solve, we see that we have an inflection point at x equals 3. X equals 3 is going to be marked on a second sign pattern underneath my first one, but I'm going to try and make the x values line up. So 3 is going to be about halfway between negative 2 and 8. if I plug in values to the left of 3, like 0, back into my second derivative, because of course it's the second derivative that defines concavity, plugging 0 in will give me 6 times 0 minus 18, or negative. So that means I am concave down. And if I plug in positive values greater than 3, like 5, 6 times 5 is 30, minus 18 is 12. That's a positive number. And so the function's concave up here. Now, let's compare these two sign patterns. It confirms that by the first derivative test, since I am changing the sign of the derivative from positive to negative, I'm getting a maximum there. And when I change from negative to positive, I'm getting a minimum, just as the first derivative test tells us. The second derivative test tells us that when we are looking at a critical point that is also concave down, that's going to be a maximum. And sure enough, it is. And when we have a critical point that is with positive concavity, that's a minimum. All right, so try and link all these themes together. We'll have more practice in class. This has been a little bit of a long video. Thanks for watching.